In this section, we're going to discuss the planets. So let's begin with terrestrial planets. The terrestrial planets are Mercury, Venus, Earth, and Mars. We will begin looking at the most important terrestrial planet, planet Earth, and see how each of the others differ from it. So this is planet Earth. Its radius is about 6,400 kilometers. Its density about 5 grams per cubic centimeter, 5 times the density of water, which is 1 gram per cubic centimeter. Has thick atmosphere of mostly nitrogen and oxygen, has active volcanoes, and has a magnetic field. All these are important ingredients for essentially life. Here's the structure of the Earth. The inner core is made of solid iron, and there's an outer core which is actually liquid, right? Mainly liquid iron and nickel, right? The mantle is mostly molten rock, silicon, and oxygen, sand in essence, right? And the crust with 30 meters is solid rock, right? And we know the structure by looking at basically waves from earthquake as it passes through the earth. So the waves basically get bent and diffracted or moved differently through the different material. And by detecting in different areas around the earth from earthquake, you can actually tell basically what's deep inside the earth. So the combination of a solid inner core, a solid iron core, and an outer liquid iron core makes the Earth's magnetic field. So without a liquid core that is in motion, we would not have any magnetic field. The mantle, which is between the core and the crust, has large magnet flows. Sometimes these magnet flows get close to the surface, which ends up giving volcanoes. Right. These flows in the mantle drag the stuff on the crust along with it, so it makes continents move over time. This is known as theory of continental drift, one of the great discoveries in Earth's geosciences. So plate tectonics, all right, or continental drift. Like plate tectonics is driven by the motion of magma in the Earth's mantle, so leads to motion of the continent over time. So for instance, there are regions basically where there might be upwellings of lava, and that forms new crust and basically forces the old crust there to basically move apart. And as it's moving apart, basically some of this crust impacts another continental crust, and so this crust ends up being forced down below. And these are called subduction zones, basically. Right? This crust will basically remelt it in the mantle eventually. Right? So the theory of paleontology comes from noticing that if you take the entire Earth, basically, and you notice that like Africa and South America kind of fit together, right? That in fact that the Earth's landmass was once one giant supercontinent called Pangaea, about 200 million years ago. And over time, basically broke up into two smaller continents, Guadaland or Laurasia, right? And these drifted apart until it formed basically the continents as we see them today, right? Um, in these regions, basically, um, mountains form basically. A lot of mountains form basically when two crusts impact each other, right? So, for instance, the Himalaya mountains comes from the fact that the Indian crust is basically hitting up against the Eurasian crust, and basically cause these mountains to fold up. Okay, uh, the Appalachian Mountains, it was actually once a mountain range even higher than Himalayas. This basically formed long ago, basically when the North America was impacting against Africa. Right. Okay. Now let's talk about Mercury and not the other terrestrial planets. So Mercury is much smaller than Earth at 2,400 kilometers. Its mass is about 5% of the Earth. Its density is about the same as the Earth. It has no atmosphere, no volcanoes, but it does have a magnetic field. Right? Mercury is very hot because it's so close to the sun. On the day side, it's about 700 degrees Kelvin, but on the night side is very cold, 100 degrees Kelvin or -200 200 degrees Fahrenheit. It's colder than pretty much any place on Earth. Because Mercury has no atmosphere, no water, there's no erosion, and so the surface is heavily cratered like the moon. Right, so this is basically Mercury's surface as seen from the Mariner 10 spacecraft. You can see a bunch of craters there. Okay, and Mercury has some unique features which are unique to it and not found on the moon. Right, it has scarps or cliffs. So here's an example of a scarp or a cliff. Right, and this comes as a result of the fact that as Mercury cools, it contracts. And as it contracts, basically, you form this hard surface, and this actually folds in on itself, kind of like wrinkles, basically, on this planet. So basically, scarps result from cooling and shrinking of the mercury, results in compression and cracking on the surface. So here's an image of a scarp, a large cliff, basically, on Mercury. Mercury has a magnetic field. It's not super strong. It's 1/100 the strength of the Earth's magnetic field. So that also means, like Earth, it must have some sort of iron core, right, or a liquid iron core, which is in motion. Next, we talked about Venus. Venus has a radius of 6,000 kilometers, just slightly smaller than the Earth. Its mass is just slightly smaller than the Earth, at 80% mass of the Earth. Its density is the same as the Earth, has a very, very thick atmosphere, possibly has volcanoes, but has no magnetic field as far as we can tell. Venus' large, thick atmosphere covers the entire surface with clouds of sulfuric acid. This atmosphere is 90 times thicker than the Earth, right? So basically, this is the structure of the Earth's of Venus' atmosphere. There's basically hazes of sulfuric acid, and with a clear layer of carbon dioxide underneath, and it's much thicker than the Earth's atmosphere. Venus is really hot. Its average temperature is 730 degrees Kelvin, which is actually hotter than Mercury. So even though it's further away, and that's because Venus' atmosphere is especially good at trapping heat via the greenhouse effect. So sunlight basically hits the atmosphere of Venus, is converted to heat, which is blocked by the carbon dioxide and the sulfuric acid from escaping back into outer space. All right. So basically, Venus is known as the runaway greenhouse effect. This will happen if you move Earth to Venus orbit. So if you move Earth to Venus orbit, the more intense sunlight will immediately raise the Earth's temperature by 30 degrees. So basically near boiling for water then, essentially. Well, not near boiling, but evaporation will be pretty substantial. The water vapor increases the greenhouse effect, further raising temperature. Okay, so water evaporates. Water is the most powerful greenhouse gas. As a result of this, basically, it would lead to more evaporation, and this warmer air holds even more water, which leads to basically a further greenhouse effect. So this is basically a runaway greenhouse effect. So eventually, after the Earth, after the oceans finish evaporating and the carbonate rocks decompose, release CO2, Earth actually becomes hotter than Venus, just because there's so much water. All right. So there's no plate tectonics on Venus. There's several possible causes. First of all, it might be very slow cooling, so very weak convection. It might be because Venus is so hot that the crust is very soft, so it doesn't crack. All right. Or it might be the fact that there's no water, so there's no lubrication, basically, which is required for subduction zones and stuff like that. However, Venus does show signs of volcanic activity. It has a young surface, not crater or anything like that. And basically, we also see change in sulfur content of the atmosphere, which is indicative of volcanic eruptions. Right. So basically, the volcanoes on Venus form from hot spots in the crust. These are so-called shield volcanoes. We have something similar on Earth, like for instance, the Hawaiian Islands are shield volcanoes. They basically form in the middle of tectonic plates. We have upwelling of magma. Right. Gula Mons is a large shield volcano on Venus. It is 4 kilometers in height and over 100 kilometers across at the summit. Right. Now let's talk about Mars. Mars is basically half the size of the radius Earth. Its mass is much lower than Earth, about 10%. Its density is also slightly lower. It's at 3.2 grams per cubic centimeter. Right, so it's smaller than Earth, but roughly density of rock. It has a very thin atmosphere. It has extinct volcanoes, and again, no magnetic field. It's called a red planet because it has a red color. This is actually due to the fact that there's a lot of actually rust, iron oxide on the Martian surface. It has a nearly 24-hour day, right, which is very similar to Earth, which is why people like to think about Mars in terms of a possible colonization site. The atmosphere is very thin. It's 1/150th out of the Earth, but it's mostly made of carbon dioxide. And also, basically, the tilt of Mars is close to the Earth, about 20 degrees, and so as a result, Mars also has seasons. Right. The atmosphere of Mars is mainly made of carbon dioxide, CO2, with some nitrogen and argon. And it's so cold, the atmosphere actually freezes near the poles as frozen CO2, depending on the season. Right. So basically, in winter, over every pole, the carbon dioxide freezes and the polar cap is much larger. So this is what I mean by seasons. So Mars dry ice cap in the winter. This is Mars's dry ice cap in the winter in the southern hemisphere. And these are seasons in Mars, basically. This is October 1996. It takes about 2 years for a season to pass, right? Then January 1997, and then March of 1997, right? So basically, the ice cap basically changes over time, right? You can see the tilt of Mars and Earth are very similar, 23.44, 23.98. Okay, the gravity is about 38% of the Mars. The Sun is about 44% of Mars. So the atmosphere is substantially smaller, right? And makeup is different too. So most of the Earth's atmosphere is nitrogen and oxygen. Most of the Martian atmosphere is actually carbon dioxide. Right. Mars actually has huge volcanoes, which are now extinct, right? So for instance, Olympus Mons is the largest volcano in the solar system and is larger than any mountain on Earth at 24 kilometers or 15 miles high. It's 3 times the size of Mount Everest. All right. These are also shield volcanoes, all right, but they're also much larger than ones on Earth and Venus, possibly because of the lower Martian gravity. Uh, the atmosphere of Mars must have been thicker in the past. It was so thick they probably support liquid water on the surface. So there's evidence of liquid water basically on the past Mars. So for instance, you see basically evidence of what looks like ancient dry riverbeds, or also etch of rocks. Basically, you see this kind of teardrop shapes. This is indicative of flowing water. Okay. What's also this is a 2003 photo of a probe on the Martian surface looking at rock that appears to be sedimentary. This is in orbit. This appears to be almost like sedimentary, right? Like rocks then laid out basically by deposition through water. Okay. This is another image basically from the Mars orbital camera, again showing basic evidence of sedimentary rocks. Okay. These little beads, right? So these berry bows is a photographed by the Martian rover Opportunity. So this underlying rock is much different composition than the Helmerlite-rich blueberries. All right. This contributes to the growing consensus that these small, strange gray orbs were slowly deposited from a bath of dirty water. Okay. The Mars's water is probably largely due to loss of space or maybe frozen down in permafrost. All right. There is some evidence in impact craters of basically some sort of flowing mud. So look at that. So the impact crater heats up the permafrost, and you see basically some evidence of flow as a result of the heated impact. Like other terrestrial planets, Mars's core has a very, very weak magnetic field. It's wrong to say it has no magnetic field, but it's really weak. So 1/800th of the Earth, right? So the core is probably still molten, but large-scale magnetic field is probably largely dormant at this point. Okay. Now Mars has always been thought of basically as a planet that could support life. So the idea of life on Mars is a very old one. The fact that Mars is so similar to Earth, especially in its early days, drove a lot of early speculation. Right. So for instance, in the 19th century, astronomers looked at Mars and believed what they saw were canals on Mars, so evidence of intelligent life. This turns out actually not to be true at all. Right. More recently, basically, a meteor was found in Antarctica. Right. This is ALH 84001, a Martian meteor with possible indication of early Martian life. This is extremely controversial because it had a mineral deposit, magnetite, and possible fossils nanobacteria, but these bacteria are significantly smaller than any bacteria that have ever been found on Earth, and so these might not be bacteria at all, but might just be natural mineral deposits. Let's move on to the Jovian planets. The Jovian planets are Jupiter, Saturn, Uranus, and Neptune. So let's start with the largest and most representative Jovian planet, Jupiter. Jupiter's radius is 10 times that of the Earth. The mass is 300 times the mass of the Earth. Its density is 1.3 grams per cc per cubic centimeter, which is about the same as water. Its components made of hydrogen and helium. There is no surface. There's an extremely strong magnetic field on Jupiter. It has very rapid rotation, about 10 hours. The weather, there's actually quite a bit of weather on Jupiter because of a very thick atmosphere. These multicolored bands you see on Jupiter are atmospheric jets. The bands are caused by convective cells that stretch out by rotation, and the most prominent feature is the so-called Great Red Spot, which is a hurricane that was first observed by Galileo and has been basically persistent on the Jupiter surface for at least 300 years now. So this is basically a little cartoon of basically how this works. So you have basically warm, the atmosphere of Jupiter is very turbulent. So you have basically stuff rising and stuff cooling, and so basically this produces different colored bands, and the solar winds end up separating these different bands from each other. The belts are the same as the high and low pressure regions on Earth. However, because of Jupiter's rapid rotation, these bends essentially stretch around the planet rather than being localized like they do on Earth. Right. So this is the Great Red Spot. Storms last hundreds of years. Right. The Great Red Spot itself is so large that you could fit 3 Earths across its long side. The inner core is most likely rocky, kind of like Earth, and the mantle is made of liquid metallic hydrogen. All right, so basically you have such high compression of hydrogen actually turns into metal. And the outer mantle is probably made of molecular hydrogen. The atmosphere is very convective with large persistent weather features. Okay. The strong rapid rotation and strong convection of Jupiter gives it a very strong magnetic field. So Jupiter's magnetic field is 20,000 times greater than that of the Earth's. And because of that, the Jupiter can actually have aurora. So Jupiter's magnetic field interacts with solar wind, which produces aurora on Jupiter, just like aurora we have on Earth, right? So interaction between the solar wind hitting the magnetic fields of Earth, basically, and then sending charged particles down, which basically produces the aurora borealis that we see on Earth. Jupiter, we see the same thing. Okay. Now, funnily, it's interesting enough, Jupiter gives off twice as much heat as it returns to the sun. Now, this heat is actually the leftover heat from heat formation 4.5 billion years ago. Jupiter is still cooling. And this cooling actually drives convection in the metallic hydrogen mantle and helps produce a strong magnetic field. Jupiter has at least 16 moons. Right now, it's actually up to 20. At least 4 of the large moons but the 4 largest were first observed by Galileo back in the 1600s, and they are named the Galilean satellites. Right. So starting from closest to furthest is Io, then Europa, then Ganymede and Castillo. Right. Okay. And these are what they're made of. They're typically rocks with some possibly lots of ices and stuff like that. As you move further away from Jupiter, you get basically more and more ices. Okay. Let's talk about Io first. Io is probably more interesting. One of the more interesting moons of Jupiter. Io is the closest of Jupiter's large moon, and it's also the most volcanically active body in the entire solar system. Right? Io is actually caught between a tug of war between Europa and Jupiter. And because of that, basically, there's a lot of friction. This gravitational tug of war that happens creates a lot of friction inside Io and ends up melting the rock. So Io's surface is really new because of all the volcanoes. There are very few craters on Io. Okay, so here's basically 2 close-ups of Io, of volcanoes on Io, basically showing plumes of sulfur and molten rock. Here's another basically picture from Galileo showing basically the red hot lava from the volcano. Okay, let's move next to Europa. Europa is the next closest moon, right? It is interesting because it is an icy surface with large cracks and no craters. That means the craters are filled in somehow. So that basically suggests that underneath this icy exterior is in fact liquid, right? So possibly water underneath this icy surface, right? So here's a close-up. Basically, there's clear evidence that there's something that's causing the surface to wrinkle. And in order to wrinkle ices, you have to have something underneath which is wrinkling it. So that's probably some water. Okay. So for the ocean underneath Io, there has to be some underlying heat source, right? So it's possible that tides from Jupiter can melt basically the ices there, right? And so as a result, basically, there's probably volcanoes or underwater volcanoes on Io. And so Io is this suggests that on Europa. So this suggests that Europa could harbor life just like that on the ocean floor on Earth, right? So if you go down to the bottom of the ocean, there are these hot hydrothermal vents, which are very, very hot water. So these hydrothermal vents are essentially boiling water. And right next to it is basically ice cold water. And in between, it supports a vast ecosystem because the ice vents provide both heat and nutrients. So it's thought that perhaps if Europa's under ice ocean is heated, then also basically could have something like hydrothermal vents underneath there and support basically life on Europa. Let's move on to Saturn. Saturn is also basically almost the same size as Jupiter compared to Earth, so 10 times the Earth's mass, 10 times the Earth's radius, 100 times the Earth's mass. Its density is significantly lower, so it's about 1.7 grams per cubic centimeter. Actually less than water, which is 1 gram per cubic centimeter. So if you took Saturn and put it in an ocean that was large enough to support Saturn, it would float. It's mainly composed of hydrogen and helium. There's no surface, but again, in this case, there's a strong magnetic field. Okay. Now Saturn is distinguished by the fact it has very, very prominent wings. In fact, all these Jovian planets have rings, but Saturn is the most prominent, right? And the rings basically have some significant divisions in it, as you can see. Now, what causes this separation are actually these tiny moons called shepherding moons, right? So here's the shepherding moon there, and you can see basically on both sides of the ring, the moon disturbs the ring. It's actually raising the stuff above, and so it's casting a shadow, All right, so this material is basically being pulled above the surface of the ring and casts a shadow basically on the rest of the ring. All right, so these are basically what's called shepherding moons. All right. Here's the structure of Saturn. It's somewhat similar to Jupiter. There's a much smaller metallic core, metallic hydrogen mantle, right? But it has a large gaseous hydrogen helium mantle, right? So the amount of metallic hydrogen is much smaller. You have much less conducting material, and so as a result, Saturn has a weaker magnetic field, 1/120th that of Jupiter, but still much stronger than that of Earth. Okay. Saturn gives off 3 times the amount of heat received from the sun, right? So this is even bigger than what's left over from formation. So in fact, what's thought to happen is that Saturn might be having something called helium rain. So basically, what happens with rain on Earth is that water vapor condenses and falls back to the Earth, and doing so basically releases potential energy. This potential energy comes as a result that the sun shines on the Earth, heats up the water, and allows it to evaporate. Now, this doesn't happen on Saturn. Instead, this is just leftover material from its formation, and if basically form helium rain, you can end up basically drive it, heating up the planet a little bit just from the release of gravitational potential energy. Saturn has a large moon called Titan, and this largest moon, Titan, is filled with oceans of methane and covered with tar, right? Has an atmosphere which is basically very naturally rich, 98%, and is only slightly thicker than Earth, so 1.2 atmospheres, right? So there's evidence of methane rain on Titan, and so perhaps there's also rainbows as well, right? Titan is cold enough that the methane will become liquid. So there are layers of liquid methane on Titan. So this is from the Cassini spacecraft, right? And as part of the Cassini mission, it dropped something called a Huygens probe into Titan. The probe was dropped on the surface of Titan, basically, and so we have basically the first picture. So this is a picture from the surface of Titan, from the Huygens probe. The first picture of a body on the surface outside the solar system. This picture is actually very interesting. This is a picture of the probe as it basically falls toward Titan. This dark spot is a lake of liquid methane. This lighter material is basically the shoreline. Right. The next is Jovian planet is Uranus. Its radius is 4 times bigger than the Earth. Its mass is 15 times the Earth. It's nearly featureless. Right. The image on the right is a false color image. Right. Made from basically taking many different wavelengths of light, ultraviolet through the infrared, and combining them together. The rotation axis of Uranus is tilted 98 degrees, so it's nearly pointing toward the sun. And so this tilt might result in a giant impact, though that's not entirely clear. Right. The next Jovian planet is Neptune. It's 4 times bigger than the Earth. It's 17 times the mass of the Earth. It has bands of clouds, unlike Uranus, which is something that does have features. It has a large storm called the Great Dark Spot. Right. The internal structure of Uranus and Neptune is slightly different than that of Jupiter and Saturn. Right. The atmosphere mainly consists of hydrogen, helium, methane gases, and the mantle consists of basically molecules like water, ammonia, methane ices, and the core itself is perhaps silicates with iron or nickel rock. So this appears to be some kind of gaseous atmosphere on top of an icy mantle and a rocky metallic core. Right. Next, we move to basically the objects beyond Neptune. These are called the trans-Neptunian objects, TNOs, right? Of which Pluto is one of them, and it belongs to basically a family of objects known as the Kuiper Belt objects. So Pluto is only the second largest of the Kuiper Belt objects. So in fact, the largest was a Kuiper Belt object known as Eris, right? So there's Eris, which is one of the Somia, and basically there's Pluto, right, with Charon, which is the big moon, and also there's a Hydra and Nix as well. Okay, and there are also other Kuiper Belt objects, Maki-Maki, Hualmei, Senya, Orcus, 2007 ORS 10, and I don't know how to pronounce that. All right, Pluto and the Kuiper Belt objects. Pluto has a large moon called Charon. So Pluto is about 1,200 kilometers in radius, and Charon is just half of that size. All right, so Pluto shares a distinction with Earth of having a large moon compared to its size. Right, the only other system which has that. In addition, Pluto has all the 2 smaller moons known as Nix and Hydra. Okay, Pluto is just one member of the Kuiper Belt. The Kuiper Belt lies between 30 to 50 astronomical units from the Sun, and consists of a large number of icy bodies that are not in the plane. So it's more like a thick disk, right? So Pluto, if we exclude it, basically orbits in the eccentric orbit, right? That is not in the same plane as everyone else. So if you contrast this with everyone else, or the other planets, basically Pluto does not belong in the same class. And this is mainly the reason why Pluto was demoted as a planet like so many years ago. There are also Kuiper Belt objects observed around other stars. So Kuiper Belt objects or debris have been found around other stars. So this is an image of Fomalhaut with a debris disk around it. And the inner edge of this disk, all right, may be due to a planet. So there's a observation of a planet basically, possibly there. Right. Now we are starting to basically see planets beyond our solar system. This is actually something which is old news now, but like when I was growing up, this was something that people speculate about. So people have speculated many years that planets exist beyond the solar system, but planets are really hard to image. So for many years, it was thought not to be possible. This started to change in the 1990s. So the first planets that were found were the pulsar planets, right? Were found around pulsar PSR B1257 plus 12 in 1992. They found 3 planets, right, from looking at timing information of this pulsar, looking at the irregularities. And as the planets move around the pulsar, they exert tiny chunks of pulse, which results in the pulse being slightly out of place. And as a result, basically, the pulses arrive slightly earlier or slightly later. Okay, so you could tell basically that there are planets around this sun. This was amazing because it was not that like these planets could not possibly survive a supernova explosion. So what happens is that they probably form after supernova explosion, right? But what we really want are planets that support life. Basically, we want planets like planet Earth. Okay, so it's important to develop techniques to be able to find planets. So here's basically a few techniques of how this might work, right? So remember, like when things orbit each other, right? They don't orbit each other. They orbit the common center of mass, right? So for instance, if it's 2 binary stars, the common center of mass is not in either one of the stars. They orbit around each other. Now, if a planet orbits a star, the center of mass of the system may still be inside the star, but it's not at the center of the star. So what will happen is the star will orbit around this common center of mass. So there are several ways to exploit this fact, right? So the first technique is known as radial velocity. So if you look at a star, right, the star gets redshifted if it moves away from you, and blue shift moves toward you, right? So if a planet orbits a star, just actually orbits a common focus or common center of mass, the center of the star will also orbit this thing, and so the star will move relative to you, away from you and back toward you again. So it'll be redshifted and blue shifted, redshifted and blue shifted. And so this can reveal the presence of a planet that poses on a star. So here's an example. So what you want to do is look at the tugs and the spectral lines of the star. So there's a planet moving around the star. All right. As the planet moves toward us, the star moves away from us and gets redshifted. As the planet moves away from us, the star moves toward us and as a result, gets blue shifted. So this redshift and blue shifting is all you need to detect the planet. All right. So in fact, this is the first technique to find a planet. Michel Mayor, who just was announced the winner of the Nobel Prize in 2019, found the planet 51 Pegasi in 1995 using this exact technique. And in fact, they didn't anticipate that it would work because they were looking for Earth mass planets, right? But basically, they found a 0.5 Jupiter mass in a 4-day orbit, which basically moves the star so much that you can just see it. So the star moves back and forth by 50 meters per second. That's almost about 60 miles an hour or so, right? Back and forth. Okay, so I mean, like a policeman with a radar detector could see this thing, right? But it's harder basically for doing planets, right? Now you can look at, if you have more than one planet, you can have basically radial velocities that look much more complicated. So this is a multi-planet system like Amstel and Andrea, and as you see in this, from this data, you could basically figure out there are 4 planets around Jupiter mass around this particular system. Another way of looking for this is so-called transits, right? So if you look for a planet, okay, sometimes the planet will eclipse the parent star. And when that happens, basically it will create a dip in the light of the planet. The dip is very small, right? It will tell you about the radius of the planet. So typical dips are something like maybe at most a percent or so, right? But typically for something like Earth, it might be really small. It might be 10 to the minus 5 or one part in 100,000 or so, right? But 1% is actually easy to do. And in fact, you can actually detect it with a good telephoto lens, right? So it turns out that this is something that's easy. And because people weren't expecting to find Jupiter planets close to the star, no one actually bothered doing it, right? But it turns out that you can actually do it with telephoto lenses. So this is an example of a transit finder. It's called HATNET, or Hungarian Automated Telescope Network. So these telescopes are actually not telescopes, not these guys out here. These are just simple telephoto lenses you can get at any camera store, right? A third technique to find planets is directly image it, right? So this is the most obvious way, but it's also one of the harder ways because the star tends to be 1 billion times brighter than the planet, right? So until recently, the only way to do it is to basically be really lucky, right? So in Fomalhaut, for instance, the planet was discovered 2008 using technique. So you basically have to block out the star and hope that the planet is far away enough that you can actually catch an image of it. Okay, so you can block out the star using something called a coronagraph. And so it's been done for the sun in many years to study the corona, which is the outer atmosphere of the sun, hence the name coronagraph. But stars are so small that it's really hard to block out their light, right? Okay. So basically, this was a major technical challenge, but in 2010, new type of coronagraph was developed, which allows stars to be precisely blocked out, and so you could basically reveal planets around it, right? These planets still have to be fairly largely separated from it, but now you can image planets directly from the ground. So these are planets around a star HR 8799. Okay. Now the final technique is something called microlensing. So remember when we discussed general relativity, Einstein's great insight was that everything moves in straight lines. You just have to change what you mean by straight, right? And so basically the curvature of space-time bends both matter and light. So light will bend as it moves around a massive body like a star or a galaxy, right? So here's basically an example of gravitational lensing. Basically, the two lights basically pass through a massive body, and the result basically get refocused to us, right? Here's a little, I guess, fun thing about gravitational lensing. Okay, so that's not really practical, right? But you see lots of evidence. You see lots of gravitational lensing in galaxy clusters. So gravity is seen around clusters of galaxies, which are the biggest objects in the universe. And you see basically here what happens. These background guns are stretched out. So this is one stretch. That's another stretch right there. Another image right there. So these are magnified by the fact that there's this big cluster of galaxies in front of these faint distant galaxies. So these are lens galaxies. Now, there's something called microlensing, right? So gravity can happen on much smaller scales, basically done by stars rather than galaxy or cluster of galaxy. In this case, light is only weakly bent, but it can make a distance appear much brighter as the lens moves in front of it. So here's an example. Here's a star, all right? If you have a planet in just the right place, all right, you get a spike. So this first spike is actually the lensing to the star. This little smaller spike is basically the lensing due to the planet, right? And so basically if you catch them at the right time, you basically watch these objects, catch them at the right time, you see that second spike, and that second spike tells you about basically both how far separated the planet is from the star and also basically how massive the planet is. Okay. So all these different techniques are useful for finding planets and give you basically different things. So for instance, radial velocity gives you the mass of the planet. Transit gives you the size of it. Direct imaging might give you size, but it's just really cool, right? Microlensing gives you mass, and for a long time, it was the only game in town for detecting something like Earth. Okay, now radial velocity can do it, and transits can do it as well. So a combination of radial velocity and transit is the most powerful technique now, right? So radial velocities were the workhorse of planet finding. In fact, they're still used to confirm planets. Because there's most sensitive massive planets, most planets are found around Jupiter masses or so, or larger. Okay. So when astronomers began first looking for extrasolar planets using radial velocity, they found there were a lot of planets with 3D orbits. So this is called a 3D pileup. So basically, these are all planets which are basically piling around 3 days for some mysterious reason, right? So what kinds of planets are found in 3 days? For the most part, these are all planets of Jupiter mass or bigger. So these are known as hot Jupiters, right? Because they're very close to the star. Okay. So how do you make hot Jupiters? Well, you can't form them there because it's well inside the snow line. We talked about snow line before. Okay. So you have to make them outside the snow line and somehow move them inward. Okay. So recall, in order to form Jupiter, you need big cores. In order to form big cores, you need basically regions where you have ices. And you have ices if you're far away from the star or outside what's called the snow line or the frost line. Okay. But however, once you form the thing out there, it can migrate inward, right? So this is known as planetary migration. And this might explain the hot Jupiter. So basically you have a giant planet and a disk of material. And as that planet moves to that disk of material, it gets slowed down. It spirals inward, closer and closer to the protostar. Okay. Now, the other big surprise when people start doing transits is that if you have transit, you can get the size of these hot Jupiters. So the second big surprise was that they're much bigger than you expect. Not by a whole lot, but just by but by enough that it's actually very hard to do. So no one has a very good explanation of why this is so, right? Now, the other interesting thing is that basically the planets in our solar system are nearly circular orbits, but this is not true of most of the planets, right? Most of the other extrasolar planets are much more elliptical orbits than solar system planets. So our solar system is a special case, right? We also saw a lot of these planets are much closer to the star than our planet, than our solar system, than the planets in our solar system. So is our solar system special, right? Well, most planets that are found are really close to the sun. Like that's totally unlike our solar system. Now this might be something called selection effect because it's much easier to find these things, right? But accounting for how to figure out the real distribution is really hard, right? Now this change was a sound known as Kepler, right? So Kepler is a mission by NASA aimed to find basically Earth-sized planets, right? And they haven't done that yet, all right? But they have found many, many interesting planets. So we find planets in configuration one thought impossible. So here's planet Kepler 16b, a planet with 2 suns, right? So for you Star Wars fans, this is Tatooine in essence. Now it was thought initially that stuff like this is unstable, right? But it turns out that if you put the planet far away from both of the suns, you're actually okay. So let's keeping our science fiction theme. There's another planet which is an Avatar planet. So basically Upsilon Andromeda. D is a possible Avatar type world. Has a gas giant in the habitable zone of basically the star, which is basically a region which is not too cold nor too hot, so liquid water can exist. So it's not to say the gas giant itself has liquid water, but the moons around the gas giant might have liquid water, i.e. Avatar. Okay. So one of the big surprises was finding a planet roughly the size in the region around the star which is not too hot nor too cold. So it's called a habitable zone, and these planets are known as Goldilocks planets. So this is a key mission of Kepler-sat, which monitors 150,000 stars to look for transit planets. Right, so it's found basically about 2,400 planets, and based on this, there could be as many as 30,000 habitable worlds within 1,000 light years of Earth. So not to say that Kepler found 30,000, but based on estimates, we can estimate how many habitable worlds are basically. So Kepler is now over, but there's a new mission taking its place called the Transiting Exoplanet Survey Set, or TESS.